So far, we've seen some of the basic numerical capabilities of R, we've seen the basic arithmetic operations, we've seen that it has a suite of mathematical functions that we can use, we've seen how we can combine these elements, and finally we have seen how we can use variables to aid our computations. In today's lesson, we're going to be looking at defining our own functions. Just as there are built-in functions in R, such as square root, exponential function, logarithms, etc., we can define our own mathematical functions. Even better, these functions will not fundamentally be different from any of the built-in functions, which means that if another user would come in and I would write a function and the user wouldn't have known that I was the author of the function and it wasn't a built-in feature of R, they would not be able to tell the difference. So our functions will function, pardon the pun, just as the built-in ones. So let us take a look. So just to recap, last time we've seen how one can use the formula that you see on the slide to compute the distance between 2 points on the surface of a sphere if those 2 points are characterized by their latitudinal and longitudinal coordinates. And the way we have approached this problem is, instead of trying to enter the whole formula as a whole, we've broken it up into simpler pieces and assigned those simpler pieces to variables called h1, h2, and h3, and then written the formula in terms of those simpler variables. And we ended up with this program, which takes the latitudinal and longitudinal data first in the variables lat1, lon1 and lat2, lon2. In this particular example, those numbers happen to correspond to the latitudinal and longitudinal coordinates of New York and London. Then we computed h1, h2, and h3, those three variables, and then in terms of those, we finally computed the distance between New York and London. Now here you will notice that this common pattern of calculating the squared sine of an angle halved appears over and over again. So it's a very natural question whether we could define this as a function. The first question would be, is it even built in to R? By the way, this function has a name. It's called the haversine function. And half of theta is equal to sine squared of the angle theta divided by 2. So that is a well-known concept. No, the answer is, unfortunately, it is not built into R. However, that doesn't really matter because we can very easily write our own function. And here is a little bit of a blueprint for how to do that. This is how we would implement the function in R. First, we write down the name of a function, just like we would do so with a variable, and then we write down the assignment arrow, again, the one composed of a lesser than symbol and a dash. And then we write down the keyword function, and in parentheses, the name of the argument. So we designate the argument of the function, which is the angle, just by calling it angle. It can be any name that is syntactically valid. You remember those naming rules. Variables can consist of letters, numbers, the period, and the underscore, and they must start with a letter. So angle is a perfectly fine name. Then there's a pair of curly braces, so an opening curly brace and a closing curly brace at the very end of the function, and in between those curly braces is where the body of the function goes. And the body of the function in this case consists of two simple expressions. The first one is an assignment. We define the quantity haversine as the sine of the angle divided by 2, and that whole expression raised to the second power. And then there's this keyword called return, and we're returning haversine. That means that this is the value the function will give back to the user. So that is the function, that is the value that the function will return, quite literally. And once we enter this and execute this in R, then we can use our have function just like any other built-in function, and nobody will be able to tell that it's any different from any of the built-in functions such as square root or such as absolute value or such as logarithms. It will work just the same. If we type in have of 0, then the computer will immediately give back the result, which is 0. If we want to compute the half of pi over 2, then again the computer immediately gives back the result, which is 1/2. So more generally, what is the pattern for defining a function? So here it is on the slide, and let me explain what it does. First of all, notice that there are these elements that are included in angle brackets. And that means that those are elements that will vary from function to function. So for example, every function has to have a name. In our previous example, it was have, short for haversign. But for different functions, we want to invent different names. The only thing to keep in mind is that the same rules apply for naming functions as for variables. If you remember those rules, those were that the name has to consist of only letters, numbers, the period, and the underscore. And the first character of the name has to be a letter. So the same is true for functions. So we find the name, then we write down the assignment operator, that little arrow symbol composed of the less than and the dash. Then we write down the keyword function, and this is one of those reserved keywords that are used for this special purpose only in R. It indicates to R that we are now defining our own function. So after the keyword function, we open a pair of parentheses, and in those parentheses, we list the inputs to the function one after the other. For example, in the previous example, if I just go back one slide, the input to the function, there was only one of them, and it was called angle. So we list all the inputs separated by commas. I should say at this point that I will use the words input, parameter, or argument to a function pretty much interchangeably. So once again, if you hear me talk about the parameter of a function, or the input to a function, or the argument of a function, I'm talking about the same thing, the thing that we put into the function that we want to operate on, and then the output is what the function actually calculates. Okay, so we put the inputs of a function in parentheses, and then we write down a curly brace. And the rest of the function goes in between an opening and a closing curly brace. So notice that the final thing in that function definition is a curly brace itself that closes the one that opens on the first line. And in between the curly braces goes the so-called body of the function, the expressions that comprise what the function does. So first we write down one or more expressions, and then we use this return keyword, and we can use that to return, to give back to the user some value. So that is the return value of the function. There are two things to be mentioned here. The first is that the curly braces are not really specific to functions in R. Instead, they have a specific syntactic meaning. Namely, expressions that are put in between a pair of curly braces are treated as if they were one single expression. And the value of that compound expression is by definition the last expression that is evaluated within the curly braces. So in other words, curly braces offer a way of pretending that the large compound expression is really just one simple expression. So that's all the curly braces are about. The second subtlety that is important to know is that the return keyword really is optional. If it is omitted, then it is by definition the last expression evaluated in the body of the function that the function will return. So we can use the return keyword because it can clarify what we do, but we don't really need to use it if we do not want to. So keeping these conventions and rules in mind, let us see some of the alternative ways in which we could have defined our earlier haversign function. So here's the definition as we've written it earlier, and let's see what kind of variations we can do on that. Well, first of all, we've just mentioned that the return keyword is optional in the sense that in case it is omitted, it is by definition the final expression in the body of the function which will be returned to the user. So that means we can simply omit the return, and instead of writing it with return, we can just write in the word haversign. That is an expression consisting of that one variable which will evaluate to itself. Its value is whatever it is computed as in the previous line, the sine of angle divided by 2 and that expression squared, and that will be returned to the user. So these two forms are completely equivalent. It's really a matter of taste which one we use. But we can even go further with this. We can actually, using the form that we've just written, that's what's at the top, argue that why go through the trouble of defining this variable haversign? I mean, after all, if the final expression in the body of the function is what's returned, then I don't really need to define it. I can just write in the sine of angle divided by 2 squared. That's an expression that evaluates to something. And because it happens to be the last expression in the body of a function, it will be the thing that is returned. So this is completely equivalent to the slightly longer form above. But if we're at this point, then why don't we go on one step further and remind ourselves that the curly braces have the role of pretending that a compound expression composed of multiple expressions is just a single expression, and its value is by definition the final expression evaluated within the curlies. But since in this particular case there is only just one expression inside the curly braces, they might as well be omitted. And therefore we end up with a much shorter definition, a much more compact version of writing the exact same function, and it will work just as well as the other versions. So it's really a question of taste which one we prefer, whether we want to be a little bit more verbose to make the function a bit more self-explanatory maybe, or we want to be a bit more compact. In this particular case, because the function is so simple, it makes sense to keep it quite compact, in my opinion at least. There's one very important principle about variables that get defined inside functions, namely the principle of locality. Notice we have the original definition for our Haversine function, the most verbose of all the options that we've had. That has return, it has curly braces, it has everything. And in that function we define a quantity called Haversine. We assign it the value of sine of angle divided by 2 squared. What you have to know is that this variable is local to the function. That is, it is invisible to the outside world. So, in other words, if we would run the following piece of code, we would calculate the Haversine of pi over 2. Then you might reason that what this does is it will execute the lines that correspond to the body of the function. So, in other words, we substitute in pi over 2 in place of angle, and then we compute Haversine as sine of pi over 2 divided by 2, and then square the result and return that. But since we've executed that line, shouldn't the variable Haversine now be defined? And the answer is, interestingly, no, it isn't, because the system takes care of keeping the variables that are defined within functions local to those functions. And that is a very useful thing to do, because it essentially allows us to treat functions as black boxes. We just give it inputs, they produce outputs, and they do not produce side effects. They do not change the world. They just give us the answers that we want. So that means that if we ask for the value of the variable Haversine after running the function have, we will just get an error. As you can see, it will tell us error, object Haversine not found, and that is because the variable Haversine, although it was defined inside the function, it only exists as long as the function itself is executing. After that, it no longer exists to the outside world. So let us take stock of our solution so far of calculating the distance on a sphere between 2 points. We first define our function have, and now, just for contrast, I've included the shortest equivalent definition that we've had, function of a variable called angle, and we simply compute the sine of angle divided by 2 squared. Then we enter the latitude and longitude data, and from those data, after that, we compute h1, h2, and h3, and notice that I no longer painstakingly type in the sine of those sums and differences divided by 2 squared. Instead, I rely on the function have that we've just defined above. And then we compute the distance at the bottom, just like we have always done before. Now, we can go on from here and define another function that we could call, for example, spherical distance. You see it at the top of the slide. And that will be a function of 4 inputs. I should have also said, or could have also said, 4 arguments or 4 parameters, mean exactly the same thing. So 4 inputs, those are the latitude of point 1, the longitude of point 1, the latitude of point 2, and the longitude of point 2. And what does this function do? That function computes h1, h2, and h3 using our earlier function have, and then returns the distance on Earth between those points using these quantities. And now that we define this function, and this is a function of 4 distinct inputs, it can be used just like any other function. The only thing to keep in mind is that yes, it will require 4 inputs. So there's an example on the screen. You can write in spherical distance and then give the latitude and the longitude of the first point and the latitude and the longitude of the second point. The first point is still New York, the second point is still London. And after that, we get the same result back as before. This function just works. There's one aspect of this function which is maybe not as elegant as it could be. Namely, notice that the radius of the sphere is what is called hard-coded. That is, we've explicitly written it into the function that it is 6,360. You might be thinking that it would be more elegant to write a function which takes yet another input, a 5th input, which is the radius of the sphere, and then we would have a function that can compute distances between points, not just on the planet Earth, but on other spheres as well, other planets, for example. How can we do that? Very easily. We simply just add another parameter to the function, just as you can see. Never you mind that I broke the line after the comma on the first line. That's just because otherwise I wouldn't have had enough horizontal space. As a reminder, in R, you can always break up an expression into multiple lines. That's part of the rule, that you can include as much white space in between different identifiers as you want. The only thing you have to be careful of is that the end of the line shouldn't suggest that the expression just ended. And in this case, because our first line ends in a comma, it's obvious that something must come after that. So we're all set and all good. So this version of the function takes another input called radius, and notice that instead of the previously hard-coded number 6,360, now we're returning 2 times radius times the arcsign of the complicated expression that will give us the distance between 2 points on a sphere. And this function works just as before. All we have to be careful with is that we need to give it a 5th input, the radius of the sphere that we're working with. You might notice that it's quite easy to get a bit lost if you have too many arguments to a function, in this case 5 of them, as for which is which. Therefore, there is a very nice feature in R which allows us to explicitly name the arguments. So, for example, in the first line that you see in the box in this slide, you see that we have the latitude and longitude data, but then for the final argument, I've named it explicitly. I said radius equals 6,360. You don't need to do this. This is completely optional, but you can do this, and it can really help you clarify which of the arguments we are talking about. Below that example, you see one where I've actually named all 5 of the inputs: lat1, lon1, lat2, lon2, and radius. So this might be even more clear than the one above. You can name as many or as few of the arguments as you wish, but the option is there, and it can really add clarity to your code. One side effect of having these named arguments is that since we give them names, the order in which they appear doesn't matter anymore. Now, that's not the case otherwise. So let's just go back to the function definition for 1 second. In this case, the function strictly is defined in such a way that the latitude of the first point is the first argument, the longitude of the first point is the second one, then comes lat2, then lon2, and then radius. And when we call the function at the bottom of the slide, then we have to make sure that we put those arguments in the correct order. But if we name one or more of our arguments, those are obvious where they go, so then the ordering doesn't matter anymore. For example, if we say spherical distance, and then we say radius equals 6,360, then that will be the first argument, and the rest will just follow the order in which they appear in the original function definition. And you see that I put it in a little comment what the order of the different arguments is. Now radius is first because we put it first, and then comes the default ordering of lat1, lon1, lat2, and lon2. There's one more thing that we can do, namely define functions with default parameter values. So it is possible, when we define a function, to say radius equals 6,360, which would make sense because most likely, most of the time, we are going to be using this distance formula to compute distances between points on planet Earth. This way, if we give it the default value, then we can omit the argument of the radius and it will simply default back to the value that we've given. So in this case, it will be perfectly valid to call the function spherical distance with only 4 inputs: lat1, lon1, lat2, lon2, and omit radius. And if we do that, then the default value will be substituted in that we've supplied when we defined the function above. I'd like to emphasize again that it could really help you to name function arguments if needed. And as an example, let us take one of the simple functions that we know quite well by now, the natural logarithm function. In fact, I have not told you this before, but the way it is defined is that it has an optional argument called base, which is set to be able to exp1, that is e to the first power, or e Euler's constant, so it is the base of the natural logarithm. So this can be overwritten, but if we do not take care to note which argument we're talking about, then we can get confused quite easily. So for example, I write down log 5, 3. Is this the base 5 log of 3 or the base 3 log of 5? And unless you're very well acquainted with how the log function works, it might be a bit difficult to tell which one it is. By the way, this is the base 3 log of 5. If you look at the top definition, you will see that that is the case, but that is not very easy to see. That is why, if we know that the second argument is called base, and it is, look up the help page for the function and you will see that it is, then it is much more clear to compute the number as log 5 and then say base equals 3. And this makes it crystal clear that we're computing the base 3 logarithm of 5 and not the base 5 logarithm of 3. So you can really help clarify your own thinking and clarify your code, both for yourself and other people who might be looking at it, by naming arguments as necessary. One final comment. As of R version 4.1, there is a shorthand notation for writing out the keyword function. Namely, it can simply be replaced by the \/ symbol. So you see 2 function definitions on the screen. And if you're using R version 4.1 or higher, then the 2 are perfectly and exactly equivalent to one another. So it's just a way to save a little bit of typing. If you don't want to type out the whole word function, you can just use the \/ symbol if you wish. The origin behind this notation, if you're interested, I've included a little bit of a link at the bottom of the slide. Feel free to check that out. It's not really important. I just wanted you to be aware that this is an option. You can use it, or if you don't want to use it, that's also fine. Just be aware that if you see this in code that is written by others, then you know exactly what it means. So that's it for today. Thank you for your attention, and I will see you next time.